Welcome back. We're going to continue our journey down part 12, dents and gouges. In particular, we're going to look at an example 12.3, and it's a level 1, the basic assessment. And originates from the API 579-2 manual, and we've taken that and we've updated it to the 2021 edition. And so we're going to go through all the steps, the basic steps for gouge assessment on a B31-3 straight pipe. Here's the problem statement. A single gouge has been found on a pipeline. Determine if the dent is acceptable without the need for repair to allow for continued operation using a level 1 assessment. The construction. First of all, it's made out of API 5L grade X42 seamless pipe. The construction code is B31-3 1999 edition. The outside diameter is 20-inch, half extra strong pipe. Joint efficiency is 1.0, so it's a seamless pipe. Or 100% RT. The allowable is 20 KSI. The ultimate strength is 60. The yield strength is 42. The Charpie has some Charpie impact test, 40 joules at minus 15, so it's got some ductility. The next thing is the process requirements. Okay, the maximum operating pressure is 6.3 or 914. The maximum operating temperature, minimum operating temperature is. Let's take a look at the inspection information. The gouge depth after dressing is 1/8 of an inch, and that's removing the work hardening from the surface. The gouge length after dressing is 12 inches. The gouge width after dressing is 1 1/8 inch or 30 millimeters. And the gouge radius after dressing is 35. The gouge angle is 30 degrees. And the following slides will talk more about that. The future corrosion allowance is 0.02 inches. The distance from the discontinuity is 1,000. So that's, in this case, I think it's a weld. The nearest, the discontinuity, that's different. That's like to a flange. The distance to the nearest weld is only 12 inches away. Again, we're going to look at table 12.2 to organize our thoughts to make sure that we clearly see things. So again, it's a piping component. It's a, let's see here. It's a piping component. It's a 1999 edition. And what we have here is the X42 pipe that we've organized the pressure, the temperature. We see that there's been no cracks found at all. So that means that we see no cracks. And we see that there was just a single gouge found. Okay, that's important. Pressurized piping, it's above ground. The gouge is located on the base metal away from the weld. And so it's on its own. No cracking originating from the gouge has been detected. And recall from our earlier videos that once you put a crack in a gouge or a dent, then this is the assessment's out the window. You've got to basically remove that crack. That's what we find in the pipeline codes. The distances are shown here. There's no history in the past of any other kind of damage in this area that we know about. And we have here our future anticipated operations. There be no change in the future. And so that's our report that should go into the assessment package. So we're going to keep going here. So we're going to go look at 12.4 again at the newest edition, assessment techniques, acceptance criterion. So we look at the level 1 and 2 is accessible based upon procedures in part 5 of thinning are provided that we have we have enough ductility, which is greater than 40 joules, or there's the work hardening material is removed. When we talked about dressing earlier, that means that we're removing, the work hardening caused by the plastic deformation of the gouge. If the CV is not known, then use 40 joules. Level 3 assessments are intended to evaluate uh, very complex geometries and transitions and such, and are subject to general loading. Okay, so or things that are subject to general loading as well. So we have here step 1, where we go to table 12.1, inspection summary required for the assessment of gouges and dents. And we're just organizing our thoughts. This is no surprise here. We looked up the allowable stress and we've organized our issues here. We know from the type of pipe what the longitudinal joint efficiency is, and it's a seamless pipe, so it doesn't apply. So we've organized all the data from the previous slide, showing the distances to the weld, and and the reason why we do this is so that we can, for my spreadsheets, I go ahead and I associate term with that, and these are the official API terminology that we would use. Going down the list, filling out the rest of table 12.1. I've included the U.S. customary units as well for our American friends, and both units, and we've organized them and attached, the symbols for each of the terms so that it's easier to sort through. And we will continue. So, for example, the gouge width after dressing, right, which is when we remove the work hardened material, is 30 millimeters, which is 1.18 inches. Typically, before we do any calculations, we go through the screening tests checks, and these screening checks are as per the 2021 edition. So we have for level 1, we have 2 sections: general checks, common to everything in part 12, and then we have a section that's specific for gouges. And there's references to part 5, which is called local metal loss, which is a close related cousin of gouges. So the first thing is in 12.2.3, for example, they say, is this a combination where there's a lot of corrosion in that area? And then you have your dent or gouge combination, and we say, well, yeah, there's no corrosion, so we say yes. Are we operating below the creep temperature? As described in part 4, table 4.1. Yes, we're operating below that. Is the component non-cyclical? Yes, because the problem didn't specifically state that there was any cyclic, so we're not doing it. I added another one. Has the flaws been removed, like the work hardened surface area been removed? And then I go to specific ones. Does it meet all the part 5 local metal loss criterion? And we go through these series of questions 5 to 5A to D, and we basically pass all those. And then we go to D 1 to 1, 2, and E, We say the level one assessment. It says type A components. Is it subject to just internal pressure only? And we say yes. And then we move on. For a level one inspection, the inspection report must consider these issues. Have we, got the dimensions as per the Part 5 procedures? Do we have the impact energies that we need? The component temperature is operating above this of a full. We're using a full specimen. There's questions about whether, that when they done the inspection, whether they've removed that locally work hardened layer that associated with that gouge. Um, do we have the material exemption curves? Do we understand that? You know, what is our minimum specified yield strength? And it has the gouge to spacing to the minor structural discontinuity, major discontinuity locations been clearly outlined in the sketches. A couple more thoughts here. Usually we do a wall thickness check by means of UT through body scan, and we get the thickness profiles, the region of metal loss needs to be identified, looking for surprises in the material. Sometimes under the surface there could be some delamination depending on the thickness of the part, of course, but we need to get a thickness profile as well. And the groove-like flaw, for flaws, we need to see exactly how it's oriented and make sure that there's no other damage in that area that we need to know about. In part 5, step 1, flaw characterization, there's some charts here that are very interesting. You can see there's some constraints that we mentioned about earlier in the earlier slides. The first one is this beta has to be less than 90 degrees, which is defined over here. And basically we just, take this is the length of the gouge G, and then we break them out into components where SL is along the axis of the pipe in this case, and C is, acting in direction circumferentially around the pipe. Now, what else can we say here? So there, basically that's it. So this is sort of another diagram that you'll see in there. And I noticed that in the problem guide that this equation solves incorrectly. Intuitively, if you're at 30 degrees, S and C should be different, but in the example, they're both the same. So just letting you know that there's a little bug in that really helpful manual. Part 5, Step 2, calculate the future wall thickness TC used in the assessment. We'll see later on that this is used quite often. There's a couple of ways to do it. There's equation 5.3 and 5.4, and to do this assessment, and then we calculate the what RT is the uniform thickness away from the local metal loss as established by thickness measurements. Again, it's so important to have really good inspection techniques. We go to part 5, step 3, where we determine the minimum thickness TMM. And basically, we use this equation, and then we determine the value of 0.38, and where the thickness TRD is described as the through thickness of the part, and DG is basically the depth. So that's how we get T min, which is over here. In step 4.1 of part 5, we determining the remaining thickness ratio. Recall we calculated earlier steps T min and over TC, and then we get this ratio. Step, we've got the longitudinal flaw length, described as lambda, and we calculate that. And notice that there's a couple of different ways of doing it. So if we have a flaw in the inside diameter of the shell, then we calculate it with this formula. And then if the flaw is on the outside, then we calculate it with that formula. And of course, d is equal to df, and we put that in equation, and behold, we get 4.5. So now we got the two critical variables that were used in level 1 assessment. This is the ratio we talked about in the previous slide in 4.1, and the longitudinal flaw length. So let's continue. Go to part 5, step 5.1, and this is where we do our screening checks to make sure that we're going the right direction with the shape of what we're doing. So we check the remaining thickness ratio. It's got to be greater than zero point 0.2. And when we do that check, last stage we did 0.75, and it's greater than zero point 0.2, so we can continue. Now we have step 5.2. In the earlier versions, like in the 2007, this calculation did not exist, and it was added to take into account the two different types of equipment. In our case, it's for piping, but this is the equation above there is for tanks and pressure vessels, and we put here not applicable. So this is where we just test the minimum thickness minus the future corrosion allowance is got to be greater than 0.05, and that's because the evaluation is not valid if it's as thin as a pop can, right? And that's basically it. So that's one of the newer additions to the specification. Part 5, step 5.3 is a very familiar one, and we've seen this in previous videos for dents, gouges, dent gouge combinations, and any other flaw. We have to check that the flaw is sufficiently far enough from a part of the vessel or tank that can stiffen the part. And so if the calculation for a level 1 assumes that that it's a flexible type of a vessel, and that's just to keep the math simple. And basically the ms the length from over here to over here, and you'd basically sum all those and you'd find the minimum one, right? And then in this case we were given that value of 1,000 millimeters, and then we compare it against this equation where we take the inside diameter at the flaw location. And I mean, you could probably iterate that for the other one in the previous slide. There was some examples, but I mean, you're still going to get 5.8, and because the 39 is greater than 5.8, so we know that the the uh, the flaw is not being stiffened by any kind of stiffness around it. And I show this here, and I mentioned this again earlier. When we talk about the distance to the toe of the weld, we refer to that line there, which is the toe, and not to the center of the weld. So you need to know the weld size. It's a little detail. Considering this calculation is quite, in this case, it didn't really matter too much because the spread is so large. Step 6, we do some more screening and we look at the geometry of that groove to make sure it meets these ideal conditions. So they have a relationship between the groove, right? The groove shown over here, over top of the ratio times the TC. So, and in this case, this is calculated to be greater than 0.5, so it's true. So this we can continue along with our level 1 assessment. We go to the B31.3 calculations, and everything is built in to the standard. You can go to Annex 2C 5.3 for straight pipe subject to internal pressure, the 2020 edition, and you can calculate the circumferential and longitudinal stresses. And we find that the minimum of those two is 979, and that's what we require, and or this is what's available, and the required is lower than that, so we pass. We will use this value here later on in the calculation to evaluate the stress. Now we go to part 5, step 8.1, and we have some choices here, but we have a cylinder. There's a couple of choices, and so we have the graph of our ratio over our lambda, which we calculated earlier. And so this is a handy chart. There's also an equation available if you want to use a calculation method, but for this we're going to do that. I have a spreadsheet. It's a bit tricky to use, and I'd recommend using the example in the example guide that can help you out with that. Make sure your calculation is correct. It's got a lot of squares and cubes in it, and that's a bit of a pain to set up. But so the maximum allowable working pressure, where we use those ratios from earlier, and we found that we're in this area, which means that we need to do a reduction in our MAWP. If we were up in this acceptable region up here, then we would be done our calculation. Okay, so let's go on to the next step. So now we're going to go into part 5, step 8.2, and this has been rearranged a little bit in the later editions, the following section. So we calculate the RSF, and if our RSF is greater than RSFA, which is the allowable remaining stress, then we have an acceptable value. If we're less than that, then we go ahead and we have to calculate from part 2, right? And so let's look at this equation. So there's something called a Mtiafolis factor, and you can get that from a table 5.2, and you put that in there, and of course your ratios there. So you can see how critical getting this RT is correct when we go ahead and we evaluate how much we have to reduce our stress by. Here's our equation, and we're going to perform an example. We look up that value of lambda, we get approximately 4.5, and you can iterate between the two if you want to get a more exact value. But we have a couple of choices. We have over here a cylinder, and which is shown right here, and we also have a spherical shell. So we get a value of 2.847. Pop it in there, and then we get an MT. We drop that value down to here first, and then we calculate RSF to be 0.82. So then we do a check. We say, well, just like the chart said, we have to do a reduction. So, and this tells us, by how much, right? So then we say, well, the local metals loss is calculated to be unacceptable, right? And because we were underneath that curve for the pipe to operate. But we can do a reduction factor. And one complaint I have is the 2007 version and the earlier versions really described this really clearly. And the 2021 version, they sort of just condensed everything together to a point where it took like about 4 reads to figure this out. So at the end of the day, it ends up being the same thing. It's just that they kind of booted it on making it nice and clean and easy to understand. So let's continue. As I said before, the 2021 version edition doesn't really explain things well. So I kind of use the same layout as the earlier version where they just had this ratio and it was super clear. And we use equation 513, and then we calculate the the reduction in the working pressure. And of course, we were looking for 979, and we can keep the system running, provided that if we can reduce that pressure down to 895. In the later versions, they added a step, or additions. They added step 9, and they really wanted to sort of like classify the different kinds of components. They went to a great deal of detail into that. So for cylindrical shells, conical shells, elbows, any components categorized in this area. We need to evaluate the circumferential extent of the flaw by adhering to the procedure shown below. So I'll just go until we stop at our example, and I'll just highlight it because we're approaching 30 minutes, so it's a long video. So in part 5, step 9.1, we just calculate this ratio of looking at the shape of the flaw, and we do an evaluation. And uh, this value here must be greater than C, and it is. So that means that we can basically we're done with this analysis. So and we can succeed with doing this analysis, and we can reduce the pressure, and we can do it with a level 1 assessment. 5, step 9.2, determine the minimum thickness necessary to accommodate the longitudinal stresses. So we would go back to step 8, and we would basically take that equation, step 8, and I use GoalSeek to determine the TLM, because you have that equation's got thickness on the numerator denominator, and then to rearrange it's a big pain in the ass. So I use GoalSeek on my spreadsheet. In part 5, step 9.3, there's some interesting things here. So we check to see whether this equation works, and if it does, then it's a pass. That's all there is to that one. And if it's a fail, then you keep going down to step 9.4. Again, the earlier versions didn't, or additions didn't carry these calculations, but we're just going to go through it and wrap this up. So they've got a part 5 here, and which is step 9.4. That's the final step. This is equation 515, and basically, if you perform this calculation, um, you can if that works, then you pass, and your evaluation passes if you go all the way down to this point here. Otherwise, you're going to have to do a level or 2 or 3 assessment is required. Let's look at the recommendations from 5423 in the 2021 edition. In the event that equipment is deemed unsuitable for continued operation according to level 1 assessment standards, the following measures or combinations may be pursued. So we can re-rate, repair the component, or replace the component or equipment. So we're looking, in our case, we did an example of a re-rate. We can adjust the future corrosion allowance by implementing remedial techniques, which would require approval by the local authority. Modify the weld joint efficiency factor through additional examination or reassessment. Say you've got some welds that they were spot done, and you can bring that up to a weld joint efficiency of 1.0. That's more common you could do on pressure vessels.